Chapter 30 is titled An Introduction to, don't say Galois, I said it there, but don't ever say it again. Galois Theory. Galois was a French mathematician who made some amazing discoveries at a very young age, by the way. I think he was about your age, 20, 21, 22, something like that. It's a sad story, though. He made these amazing discoveries, and then he died in a duel very shortly after. I think the story goes the night before he died in the duel, he did write a lot of math, hoping that his work would carry on. And maybe that's why he died in the duel, is because he was too tired. I don't know. But anyway, sad story. The duel was over, I think, maybe a mixture of politics and vying for the affections of some woman, and he lost. Anyway, the Galois theory is about, well, relating group theory and field theory in the abstract, though his purpose was not to relate group theory and field theory, because he didn't know about groups and fields in the abstract as we know about them. Instead, he was thinking about a particular problem, trying to solve the general quintic equation, fifth degree. We can solve linear equations very simply, right? Just solve ax plus b equals 0 for x very simply. Quadratic with quadratic formula. Cubic equations have a formula as well, but it's much more complicated. Quartic, fourth degree equations have a formula as well, but it's really complicated. Maybe on Friday, I'll show you Mathematica's solution of it. No time for it today. Fifth degree, okay, just keep upping the degree. Is it solvable by radicals or not? Can you use square roots, cube roots, fourth roots, fifth roots, and some, linear combination of those things, finite number of steps to get roots of fifth degree equations? And Galois proved you can't. Okay, there's another mathematician named Abel for abelian groups who also was part of that. But this is about Galois theory and something called the fundamental theorem of Galois theory. I'm not going to read through this, but let's start struggling or wrestling with some definitions and some examples to get a little feel for what this is about. So right off the bat, we start with a challenging definition right here. Get our bearings. It says, let E be an extension field of S. So we could start making a drawing, and that feels fun for a few seconds. And all of a sudden you realize, well, the drawing's a tiny bit helpful, but not super helpful, right? E is an extension field of F, so F is a subfield of E. And you could draw a diagram like that to illustrate that. And that makes you feel happy, like I said, for a few seconds, but then you look at the rest of it and you're like, okay, maybe I'm not so happy. Next sentence, an automorphism of E. Oh, there's that word again, automorphism. What was an automorphism in group theory? An automorphism in group theory was a group isomorphism from a group to itself, auto meaning self. An automorphism of a field E is a ring isomorphism from E to itself. E is a field, but remember, fields are rings. So it's not a problem to call it a ring isomorphism. But again, from E to itself. The Galois group of E over F, written like this, Galois of E over F, by the way, has nothing to do with quotient groups or quotient rings here. I guess I should say factor groups or factor rings, is the set of all automorphisms of E that take every element of F, the smaller field, to itself. So an automorphism of E maps E to E. Maybe you could just draw a little arrow like this and a phi, indicating phi maps E to E. But phi being in this Galois group, yes, it does mean phi is an automorphism of E, but it also means, this implies phi of A equals A for all A in the base field F. It fixes all elements of F, sends every element of F to itself. When you read something like this, first thing that should pop in your mind is, well, why is that a group, for example? It's called the Galois group. Why is that a group? Well, go back to the definition of a group. You got a binary operation. What would it be here? Let's just talk about this verbally here initially. You got a binary operation. What would it be? It would be function composition, right? The elements of this thing are functions. Typically, at least with group theory, the group operation when your set is functions is function composition. Like, think about the dihedral group examples, Dn, or the symmetric group Sn. The elements are functions and the group operation is function composition. It's got to be associative. Well, function composition is always associative. That's the second thing. Got to have an identity. What would be the identity? What did we call it back in group theory when it was functions? What was the symbol we used? Into its Greek letter. Epsilon. It's got an epsilon. What is epsilon? It's the function that maps everything in E to itself. Will that fix the base field F? Sure. If it maps everything in E to itself, it's going to map everything in F to itself. Inverses. You got an automorphism from E to itself that fixes everything in F, maps everything in F to itself. Does its inverse function map everything in F to itself? Certainly the inverse function exists. If I assume phi is an automorphism of E, that means it's a ring isomorphism from E to itself. Isomorphism, yes, it means operation preserving, doubly so, but also one-to-one and onto. It's got an inverse function. We have seen in the past that the inverse function will also be operation preserving. It will be a ring isomorphism from E to itself. Does it fix everything in F? Well, if phi of A equals A for all A in the base field F, the smaller field, effectively by applying the inverse to both sides, you could say phi inverse maps everything in F to itself. This is the kind of thing that's going to be very helpful for you as you work through reading, if it hasn't to this point. And even though it's almost the end of the semester, it's not too late to start. You've got a couple days here, the last week of class. You got next week, finals week, to continue studying this stuff. It's still worthwhile for you to spend time. Now, of course, if you're studying late at night and you're really tired, or early in the morning and you're really tired, that's tough to do. But that's what's going to most benefit you. I know it slows you down. Yeah, it slows you down in the short run. It actually saves you time in the long run, at least if you've got to put in enough time to get the grade you want. So it's worthwhile. It is a group, is the point here. Next sentence. If H is so this is a separate definition. There's really a couple definitions in this paragraph here. If H is a subgroup of the Galois group of E over F, the set E sub H, what's that? That's the set of everything in E such that phi of X equals X for all phi in H. So again, here's the situation with the fields. This would be like the field situation. Fields. You got the corresponding groups. You got the Galois group of E over F. And you got this subgroup H. H is not just a subset of the Galois group, but it's a subgroup of the Galois group. It consists of certain functions that are ring automorphisms, field automorphisms, you can call it, from E to itself, that fix everything in F. It's a subgroup of that. It is a group itself under function composition. EH would be all the things in E, the bigger field, that get mapped to themselves under everything in H. Certainly everything in F would be in EH, right? Think about that. Everything in the entire Galois group is going to map everything in F to itself. So certainly everything in H will map everything in F to itself. But it could be bigger. It could include elements of E that are not in F. Maybe this is the EH. There could be elements in E that are not in F that get fixed by elements of H. Functions in H map these things to themselves. But there are some functions in the Galois group that don't. Does that make sense? That's conceivable that EH could be somewhere in between. It's called the fixed field of H. That should bring up another question. Is it really a field? Is EH, by this definition, really a field? It's certainly a subset of E. Is it a subfield? Think about that. It would be a subfield if it's also a subring, because fields are rings. Really, you could try to use the subring test on EH. Verify it's closed under subtraction, and verify it's closed under multiplicative inverses. For example, if you've got two elements, A and B, in EH, is there difference in EH? What would it mean to be in EH? It means phi of that thing, or of A minus B in this case, equals A minus B for all phi in H. Okay, it's going to be pretty simple. Just use the operation preserving property of automorphisms. Then use the fact that you're assuming A and B are in EH. This is going to be true for all phi in that subgroup. Probably a better way to say this, to phrase this, if you were writing this as a proof, is you'd say let phi be in H. Let phi be in the subgroup groups so that you know phi of A equals A and phi of B equals B. And then you could say this is true. That phi would fix A minus B, and that would mean A minus B is in EH. How about undertaking inverses, or more generally, products of this form, say A, B inverse? Once again, use the operation preserving property. This is ultimately phi of A times phi of B inverse. If I assume A and B are fixed by elements of H, that's going to be A, B inverse. So there's nothing too much to prove, but technically it does take short proofs to verify EH is a field. Right? So we're starting to get a little feel for working with the definition. Of course, abstract definitions by themselves for most people are not enough for understanding. That's true, by the way, for 99.999% of all people. We also need examples. So we look to the next page to start working through examples. By the way, the beauty of Galois theory is supposed to be in these diagrams, these lattice diagrams. This one is a lattice or tower of fields. This one is a subgroup lattice for a Galois group. There are interesting relationships between these diagrams. That's the essence of the fundamental theorem of Galois theory. But let's look at some examples. Start with example 1. We've seen that field extension before. Q adjoining root 2 is a field extension of Q, the rationals. Remember, as I've said before, it's not just taking the rationals and adding one number, square root of 2. It is the smallest subfield of the complex numbers, or you could also describe it as the smallest subfield of the real numbers. that contains all the rationals and square root of 2, but it contains plenty of other numbers. For example, 2 square root of 2, or 3 square root of 2, or even 1/2 square root of 2. You can prove that it equals this set. When you see this kind of thing, remind yourself of other things that it means. We're essentially writing every element of this field as a linear combination of the number 1 and the number square root of 2, where the coefficients, the scalars, are rational numbers. It's a vector space over the base field, over the rationals, with a basis having 2 elements, 1 and square root of 2. 2 quote-unquote vectors, though we're using the word vector there in a more abstract way than you have typically learned about. It's got dimension 2. The degree of this extension is 2. Are 1 and square root of 2 linearly independent? Yes, that takes some proof. It's not a difficult proof, but it is true. This is claiming spanning right here. Says, since that's true, and any automorphism of a field containing Q must act as the identity on Q, exercise 1. Maybe we should do exercise 1. But let's see what their point is. An automorphism of phi of this thing is completely determined by phi of root 2. Before going on, maybe we should try to understand what they mean by that. What does it mean? It's completely determined by the value of phi of root 2, based on the fact that they're saying such an automorphism must act like as the identity on Q. Assuming that's true, assuming we proved exercise 1, why is this last phrase true? Why is it completely determined by the value of phi at root 2? Here's the reason. If you plug in an arbitrary element of the field Q adjoining root 2 into such an automorphism, the fact that the automorphism's operation preserving allows us to write this, first of all, using the fact that it preserves addition, and it also preserves multiplication, so that allows us to write this. Any such automorphism would have this property. The claim of exercise 1 is that everything in the rationals, the A and the B, get fixed by such an automorphism. Phi of A must be A and phi of B must be B. A and B are rationals. And look at this formula. We'll look at this property. Phi of such an element must equal that. That's why the answer, what this automorphism is completely determined by what the value of that is. This begs a question, though. What about exercise 1? Why do automorphisms of field extensions of the rationals fix all the rationals, map every rational to themselves? That is what exercise 1 says. Let's quick look at it. Exercise 1 says, let E be an extension field of the rationals, any extension field, I guess. Show that any automorphism of E acts as the identity on Q, fixes Q, maps every rational number to itself. That's exercise 1. Doesn't sound so easy to prove, does it? Let's think about the scratch work for proving that. Maybe we should build it up in steps. Certainly, integers are rational numbers. And the simplest kind of integers to think about are positive integers. If phi is going to map every rational number to itself, it should certainly map every positive integer to itself. Let's pretend that this is in the positive integers. Z plus means positive integers. How could I prove that an arbitrary automorphism of a field extension of the rationals maps a positive integer to itself? Doesn't seem so clear, does it? Here's the key thing. Since m is a positive integer, I could write it as 1 plus 1 plus 1, etc., with m terms there, m summands. And that should remind you to use the fact that phi is operation preserving probably now. Right? You always want to use, when you're working with isomorphisms, homomorphisms, automorphisms in this case, you always want to use the fact that they're operation preserving. That's the whole key to it. You always want to use that. So that would mean this is phi of 1 plus phi of 1 plus phi of 1, etc. Also with n summands. In other words, you could say it's m times phi of 1. But what's phi of 1? It's 1. Why? We know that about ring homomorphisms or isomorphisms from a ring with unity to itself, and fields have unity. They got to map 1 to 1. That was a property of field isomorphisms. Therefore, phi maps m to itself. So there's how you do it if m is a positive integer. You might wonder about, well, what if m is a negative integer? Call it negative m. Pretend m is positive, so negative m is negative. Use the fact that it's operation preserving. You could pull the negative sign out. And now use the fact that you proved phi maps positive integers to themselves. Phi would also map 0 to itself, right? Even homomorphisms map the additive identity to themselves. Or the additive identity to the additive identity. In this case, it's the same additive identity because it's a field automorphism. All right, well, what about fractions? Maybe we should do the simplest kind of fraction first, like 1 over m. Where m is non-zero. M is a non-zero integer. Z take away 0. Well, that's the same as phi of m inverse. And being operation preserving means that's the same as phi of m inverse. And phi maps m to itself. M is an integer. That's m inverse, or 1 over m. And finally, what about an arbitrary fraction? Call it m over n, where we're not dividing by 0. The way you'd want to think of it is m times 1 over n, or, okay, I could write that as an n inverse. But use the operation preserving property and use the facts that you've just proved. And you'd be done. So there is a quick verbal, with some equations, proof that of number 1. I wrote some equations and I verbally said why this proves it all. Okay, if you're really going to understand the reading, when you encounter something like that, it says see exercise 1 or see some other exercise, you really should, if you want to fully understand it at least, try to do the exercise. This is at a level, these things are at a level you should be able to do for the exam. Coming back to the example, we're not done with the example. Where are we so far? We are to the end of that sentence there. So it's completely determined by phi of root 2. Thus, what are we doing here? 2 equals phi of 2. Why? Because 2 is a rational number. It's an integer, therefore it's a rational number. Therefore, phi maps it to itself. And yes, 2 is root 2 times itself, root 2 squared, and then phi is operation preserving. Phi of root 2 times root 2, it must be phi of root 2 quantity squared. In other words, phi of root 2 must be plus or minus root 2. Those are the two possibilities, the only two possibilities. This proves the group has two elements, the identity mapping and the mapping that sends a plus b root 2 to a minus b root 2. Okay, the author actually overstated the case there. If phi of root 2 equals root 2, then phi will be the epsilon, will be the identity mapping, because back here you will replace that with root 2, and we've already seen the identity mapping. The epsilon is a field automorphism in the Galois group, fixes the base field. But the author hasn't fully proved that if it maps it to a minus b root 2, that is also a field automorphism in the Galois group, fixing the base field, which is Q in this case. Is that hard to prove? Define phi from Q of root 2 to Q of root 2, that field extension of Q, by the equation phi of a plus b root 2 equals a minus b root 2. In saying this proves this, the author is expecting you to fill in some details. What kind of details? Well, is this function one-to-one? Is it onto? Is it doubly operation preserving? And does it fix the base field Q? Those things are all true, but technically need proof. One-to-one. Suppose phi of a plus b root 2 equals phi of c plus d root 2. That'll imply a plus b root, or excuse me, a minus b root 2 equals c minus d root 2. And yeah, the only way that happens, the only way these can be equal is if a equals c and b equals d. So that a plus b root 2 equals c plus d root 2. Now, the only questionable implication here is that one. Does that really imply for sure that a equals c and b equals d? I mean, it seems reasonable. That technically takes proof too. It's related to the fact that 1 and root 2 forms a linearly independent set over the rationals. Okay, if you want some details there, you could say this implies a minus c times 1 plus negative b plus d times root 2 equals 0, and use the linear independence of 1 and root 2, assuming you prove that. This would imply a minus c is 0 and negative b plus d is 0. And that would imply this. Linear independence is what I'm really using. Question? Yes, yes, thank you. There should be a C here. Is it onto? Given a plus b root d in Q root 2, can I find what gets mapped to it? Yeah, a minus b root 2 will get mapped to a plus b root 2. Because a minus b root 2 is the same as a plus negative b root 2. That gets mapped to a minus negative b root 2, which is the same as a plus b root 2. Is it operation preserving with respect to addition? Take two elements, a plus b root 2 and c plus d root 2, and add them. Add the parts that don't involve the root 2. The like terms effectively. Add the parts that do involve the root 2. What does that get mapped to? It gets mapped to a plus c minus b plus d root 2. By properties of algebra, that can be rewritten as a minus b root 2 plus c minus d root 2. And that's phi of a plus b root 2 plus phi of c plus d root 2. That does it. I know I'm going kind of fast. These are all certainly calculations you should be able to do, understand fairly quickly, hopefully not make a mistake like I did with the one example at first. Does it preserve multiplication? That's a little trickier. First, multiply these out. You got a FOIL. And kind of like using the fact that I squared is -1 when you multiply complex numbers, use the fact that root 2 squared is 2 when you multiply these kinds of numbers. So it's the first and last products that are going to give you something that does not involve root 2. There's a times c, and there's also 2bd, right? Because last times last would be b times d times root 2 squared. And the parts that do involve the square root of 2 and it doesn't go away are the outside and inside products. And the coefficient is going to be AD plus BC. That's going to then equal, by the formula for phi, AC plus 2BD minus AD plus BC root 2. That should equal this product. Does it? You actually have to do it. First, what is phi of those things? It's these things. Multiply it out. You will get that. They are equal. Do it in your head. The part that does not involve root 2 comes again from the first and last products. First times first is AC. Last times last is positive. The two negatives make a positive, 2BD. And then with the outside and inside products, you factor out the root 2. You also factor out a negative sign. You will get the exact same thing. Finally, does it fix Q? Given A and Q, which is a subfield of Q adjoin root 2, and phi in the Galois group, well, phi being this function, what is phi of A? Well, use the fact that A can be thought of as A plus 0 root 2 to give you A minus 0 root 2, which is just A. Phi does map A to itself. Actually, we already knew that by exercise 1 because any automorphism of field extension of the rationals will fix all the rationals. We already knew that. Not just for this particular field extension. By the way, that's not true for when your base field is not the rationals. It's a very special property of the rationals. Not true in general, at least, unless you assume it's in the Galois group to begin with. Assuming it's in the Galois group means it automatically fixes the base field. That's the assumption of being in the Galois group. The textbook stops example 1 right there. Let me go a little further, say something else. What have we just done? We verified that this Galois group of Q adjoin root 2 over Q has two elements, epsilon and phi, where phi, epsilon is the identity mapping of Q root 2 to itself, and phi is the function that we were just working with, mapping A plus B root 2 to A minus B root 2. It's a two-element group, therefore it must be cyclic of order 2. It's isomorphic to Z2. And if you were going to make a lattice of subgroups of this, it'd be very simple. The subgroup lattice would be a picture like this, epsilon phi up there, that's the whole group, and then you've got the trivial subgroup, just epsilon. A very simple subgroup lattice. You could label this line with the number 2 representing the index of the subgroup in the bigger group. There would be 2 cosets, It's trivial that this is the case. Because that's the trivial subgroup right there. It's only got one element. The number of left cosets of that in the bigger group would just be 2. Epsilon by itself and phi by itself would be the cosets. The factor group, when you're factoring out by the trivial subgroup, would be the isomorphic to the original group. It would be also isomorphic to Z2. And then coming to the fields in question, you could call it the field lattice. I prefer calling it a tower of fields. Field lattice consists of Q adjoining root 2 being a field extension of Q of degree 2. 2 would be the degree of Q of root 2 over Q. What does degree mean? That's the dimension of Q of root 2 as a vector space over Q, right? Basis of 2 elements. We've already talked about this, 1 and square root of 2. These diagrams are very similar. These are related, it seems. They're the same kind of diagrams pictorially, including the number 2. That picture, that relationship between the diagrams generalizes to more complicated situations like this one. Wow. In certain special situations, at